Introduction.
Don't scrub, Ankush. Let me study.
What are you studying?
I'm doing my homework of chemistry.
You are doing wrong.
What are you doing?
Now this is correct.
No, this is double bond and this is an alkene.
Teacher has taught us about single bond and alkanes, but she did not teach alkenes. What are they?
Alkenes are unsaturated hydrocarbons, and so are alkynes. Come, I'll tell you in detail about alkenes and alkynes.
Objectives. At the end of this lesson, you will be able to explain alkenes and alkynes, name alkenes and alkynes according to IUPAC system of nomenclature, recognize and write structures of isomers of alkenes and alkynes, learn methods to prepare alkenes and alkynes, write the physical and chemical properties of alkenes and alkynes. Alkenes. Alkenes are class of hydrocarbons which contain only carbon and hydrogen. Two other terms which describe alkenes are unsaturated and olefins. Unsaturated hydrocarbons contain either double or triple bonds. Since the compound is unsaturated with respect to hydrogen atoms, the extra electrons are shared between two carbon atoms, forming double bonds in alkenes. Alkenes are also called olefins because they form oily liquids on reaction with chlorine gas. These are the compounds of ethene or ethylene and pentene. Structure of double bond. The chemical bonding in alkenes can be illustrated by reference to the simplest alkene, ethene. Ethene is not a very complicated molecule. It contains two carbon atoms that are double bonded to each other, with each of these atoms also bonded to two hydrogen atoms. This forms a total of 3 bonds to each carbon atom, giving them an sp2 hybridization. Since the carbon atom is forming 3 sigma bonds instead of the 4 that it can, it only needs to hybridize 3 of its outer orbitals instead of 4. It does this by using the 2s electron and 2 of the 2p electrons, leaving the other unchanged. This new orbital is called an sp2 hybrid because that's exactly what it is. It is made from one s orbital and 2 p orbitals. When atoms are an sp2 hybrid, they have a trigonal planar structure. These structures are very similar to a peace sign. There is a central atom with 3 atoms around it, all on one plane. Trigonal planar molecules have an ideal bond angle of 120 degree on each side. The HCH bond angle is 117 degree, which is very close to the ideal 120 degree of a carbon with sp2 hybridization. The other two angles, HCC, are both 121.5 degrees. Nomenclature of alkenes. Step 1. Find the longest continuous chain that includes the double bond. Step 2. Use the ending end to indicate the presence of carbon-carbon. Step 3. Number of the chain so that the first carbon of the carbon-carbon reached has the lowest possible number. Step 4. Name and number substituents in the same fashion as in alkanes. This is 1-butene and these are 2-methyl-2-butene and 3-methyl-1-butene. Step 5. The alkene functional group takes precedence over alkyl and halide functional groups. Step 6. The alcohol functional group takes precedence over the alkene functional group. 4-bromo-3-methyl-1-butene. Nomenclature of alkenes, Part 2. Step 7. Hydroxyl groups takes precedence over the double bond when the chain is numbered. This compound is 2-methyl-3-butane-1-ol. Step 8. If more than one double bond is present, indicate their position by using the number of the first carbon of each double bond and use the suffix diene for 2 double bonds, triene for 3 double bonds, tetraene for 4 double bonds, etc. For example, 1,4-pentadiene. Step 9. Cycloalkenes are named in a similar way. Number the cycloalkene, so the double bond carbons get numbers 1 and 2, and the first substituent is the lowest possible number. If there is a substituent on one of the double bond carbon, it gets number 1. 6-ethyl 1-methyl cyclohexene. Look at this compound. It is named as 1,5-dimethyl cyclopentene and not 2,3-dimethyl cyclopentene. Isomerism. Structural isomerism. All the alkenes with 4 or more carbon atoms in them show structural isomerism. This means that there are 2 or more different structural formulae that you can draw for each molecular formula. For example, with C4H8, it isn't too difficult to come up with these 3 structural isomers. There is, however, another isomer, but-2-ene, also exhibits geometric isomerism. Geometric cis-trans isomerism. The carbon-carbon double bond doesn't allow any rotation about it. That means that it is possible to have the CH3 groups on either end of the molecule locked either on one side of the molecule or opposite each other. These are called cis-but-2-ene, where the groups are on the same side, or trans-but-2-ene, where they are on the opposite sides. Cis-but-2-ene is also known as Z-but-2-ene. Trans-but-2-ene is also known as E-but-2-ene. Preparation of alkenes, Part 1. Alkenes are generally prepared through beta-elimination reactions, in which 2 atoms on adjacent carbon atoms are removed, resulting in the formation of a double bond. Alkenes are usually prepared from either alcohols or haloalkanes, alkyl halides, by the dehydration of alcohols. In dehydration reactions, a molecule of water is eliminated from an alcohol molecule by heating the alcohol in the presence of a strong mineral acid. A double bond forms between the adjacent carbon atoms that lost the hydrogen ion and hydroxide group. From haloalkanes or alkyl halides. Alkenes can be obtained from haloalkanes, alkyl halides. These haloalkanes are usually bromo and iodo and less commonly chloro derivatives. Preparation of alkenes, Part 2. By dehydrogenation of haloalkanes. Haloalkanes on heating with alcoholic potash loses one molecule of hydrogen halide to give alkene. Bromoethane gives ethane. Dehalogenation. Vicinal dihalides, which are alkane molecules that contain 2 halogen atoms on adjacent carbon atoms, can form alkenes upon reaction with zinc. From alkynes. Alkenes can be easily obtained by hydrogenation of alkynes. An alkyne on controlled hydrogenation with hydrogen in the presence of Ni or Pd at 200 degrees centigrade gives corresponding alkene. Ethine gives ethene on hydrogenation. Physical properties of alkenes. Physical state. Alkenes can exist in all the 3 physical states, gases, liquids and solids at room temperature. At room temperature, lower alkenes, first 3 alkenes, are colorless gases, while next 14 members, those comprised of 5 to 15 carbon atoms, are colorless liquids. The higher alkenes are colorless solids. Except ethene, all other alkenes are colorless and odorless. Ethene has a faint sweet smell. Because of non-polar nature of alkenes, they are insoluble in water, but soluble in non-polar solvents like benzene, carbon tetrachloride and petroleum ether, etc. Density. Alkenes have densities less than 1 gram per milliliter and are therefore less dense than water, hence form separate layer above water. As the molecular mass of alkenes increases, density increases. Boiling points of alkenes. In liquid state, molecules are packed closely together with weak intermolecular force of attraction, hence can be moved randomly in system. When we supply heat to the liquid, temperature of system increases, which contributes in the increment in kinetic energy of molecules. Hence, the molecule motion increases and the forces of attraction between the molecules decreases at high temperature. Just like boiling point, melting points of alkenes also increase with an increase in the molecular mass. Chemical properties of alkenes, Part 1. Alkenes are more reactive than alkanes due to the presence of a double bond. The carbon-carbon double bond consists of a strong bond and a weak p bond. Addition reactions. The p electrons of the carbon-carbon double bond are available to an electrophile, any species seeking electrons. Thus, the addition reactions shown by alkenes are in fact electrophilic addition reactions. Addition of hydrogen. Alkenes add hydrogen in the presence of platinum or nickel catalyst to form alkanes. The reaction termed as hydrogenation is an exothermic reaction. Addition of halogens. Alkenes react with halogens to form dihaloalkanes. The order of reactivity is chlorine is greater than bromine is greater than iodine. Simply mixing together the two reactants, usually in an inert solvent like carbon tetrachloride, best carries out the reaction. Addition of halogen acids. Alkenes with concentrated aqueous solution of halogen acids give haloalkanes. The order of reactivity is Hi is greater than HBr is greater than HCl. In asymmetrical alkenes, the addition of a halogen acid takes place in a manner whereby the halogen atom, the negative part of the molecule to be added, adds to the carbon atom, which has lesser number of hydrogen atoms on it. For example, in the case of propene, the product obtained is 2-iodopropane and not 1-iodopropane. This rule of addition of halogen acids to an asymmetrical alkene is known as Markovnikov's rule. Chemical properties of alkenes, Part 2. Addition of sulfuric acid. In accordance to Markovnikov's rule, alkenes readily add concentrated sulfuric acid to form alkyl hydrogen sulfates. For example, ethene react with ethane sulfuric acid to give ethyl hydrogen sulfate. Addition of water, hydration of alkenes. Water molecules add to an alkene molecule across the double bond in the presence of dilute acid and a catalyst. For example, ethane gives ethanol when a mixture of ethene and steam is passed over phosphoric acid and silica under a pressure 65 atmosphere and at 300 degrees centigrade. Addition of ozone. Ozonides are formed when alkenes add a molecule of ozone across the double bond. For example, ethene gives ethene ozonide. Polymerization. Addition polymerization is a process by which a large number of molecules of the same species join together without the elimination of simple molecules like HX, H2O, etc. to form a giant molecule called a polymer. Alkenes undergo addition polymerization when heated under pressure in the presence of suitable catalysts. When ethene is heated to 1000 degrees centigrade under 1000 atmospheric pressure in presence of oxygen, we get polyethene. Alkynes. Alkynes are hydrocarbons which contain a triple carbon-carbon bond. As with alkenes, the simplest member of the series is 2-carbon molecule. The triple bond is indicated by changing the ending of the name to "-ine", in the same manner as the double bonds in alkenes are indicated by the ending "-ene". Alkynes, like alkenes, are unsaturated hydrocarbons with the general formula CnH2n-2. They are very unstable and quite reactive. For example, ethyne, the simplest alkyne, which is more commonly known by its common name acetylene, is a gas often used as a fuel for cutting and welding torches because it burns with a very hot flame. Naming alkynes. In IUPAC system, the alkynes are named as derivatives of alkanes. The suffix "ane" is replaced with "ine" in the alkane name. For example, the given compound has 3 carbon atoms and hence the root name is propane. If the suffix "ane" is replaced with "ine", we will get the IUPAC name of the compound as propyne. If there is a substitute in the chain, the longest chain is selected in such a way that the chain contains the triple bond. Similarly, the chain is numbered in such a way that the carbon containing the triple bond gets the least number. For example, the given compound contains 5 carbon atoms in the longest chain, hence it is named as pentyne. It is named from the right to left so that the carbon containing triple bond gets the number 1. There is one substitute methyl group at third carbon atom, hence the name of the compound is 3-methyl-1-pentyne. Structures of alkynes. In the structure of alkynes, the carbon atom undergoes sp hybridization. The outermost electronic configuration of carbon is 2s2 2p2. In the excited state, one electron from 2s orbital is excited to 2p. Hence, the electronic configuration in the excited state is 2s1, 2px1, 2py1, 2pz1. Here, the carbon undergoes sp hybridization to give 2 sp hybridized orbitals with linear shape and with bond angle as 180 degrees. One of the sp hybridized orbitals is connected with other carbon and other is connected with hydrogen. Hence, the structure of acetylene molecule is linear. Isomerism. Chain isomers. Compounds having same molecular formula with different in carbon chain pattern like linear or branch are called chain isomers. 1-pentyne is chain isomer of 3-methylbutane. Position isomers. Compounds having same molecular formula with difference in position of the functional group are called as position isomers. 1-butane and 2-butane are position isomers. Functional group isomers. Compounds having same molecular formula with difference in nature of functional group are called as functional group isomers. Alkynes are functional group isomers for cycloalkenes. For example, pentyne and cyclopentene are functional group isomers. Geometrical isomers. The bond between carbon atoms in alkyne is rigid and cannot be rotated. Hence, there should be possibility of geometrical isomers. But the orientation of atoms cannot be determined. Hence, there is no possibility of geometrical isomerism in alkynes. Preparation of alkynes. The preparations of alkynes are very similar to those of the alkenes. The main preparative reactions involve the elimination of groups or ions from molecules, resulting in the formation of pi bonds. Dehydrohalogenation. The loss of an hydrogen atom and a halogen atom from adjacent alkane carbon atom leads to the formation of an alkene. The loss of the additional hydrogen and halogen atoms from the double bonded carbon atoms leads to the alkyne formation. The halogen atoms may be located on the same carbon, a geminal dihalide, or on adjacent carbons, a vicinal dihalide. During the second dehydrohalogenation step, certain conditions are necessary, namely high temperatures and an extremely strong basic solution. Dehalogenation. Vicinal tetrahaloalkanes can be dehalogenated with zinc metal in an organometallic reaction to form alkynes. Substitution. Larger alkynes can be generated by reacting an alkyl halide with an acetylide ion, which is generated from a shorter alkyne. Ethyne acetylene preparation. Ethyne, which is commonly called acetylene, is the simplest alkyne. Historically, it was prepared by reacting calcium carbide with water. Today, ethyne is normally prepared by the pyrolysis of methane. In this procedure, a stream of methane gas is briefly heated to 1500 degrees centigrade in an airless chamber. Air must be excluded from the reaction or oxidation combustion will occur. Physical properties of alkynes. The physical properties of alkynes are very similar to those of the alkenes. Alkynes are generally non-polar molecules with little solubility in polar solvents, such as water. Solubility in non-polar solvents, such as ether and acetone, is extensive. Like the alkanes and alkenes, alkynes of 4 or fewer carbon atoms tend to be gases. Substituted alkynes have small dipole moments due to differences in electronegativity between the triple bonded carbon atoms, which are sp hybridized, and the single bonded carbon atoms, which are sp3 hybridized. The sp hybridized carbon atom, which possesses more s character than the sp3 hybridized carbon atom, is more electronegative in character. The resulting asymmetrical electron distribution in the bond between such carbon atoms results in the generation of a dipole moment. Chemical properties of alkynes. Combustion. Alkynes burns in air or oxygen with smoky flame. Addition of hydrogen. An alkyne reacts with hydrogen in the presence of catalyst, Pt or Ni, at 250 degrees centigrade, first forming alkenes and finally alkanes. Addition of halogens. Alkynes react with halogens, Cl2 or Br2, in the dark, forming dihaloalkanes, first and finally tetrahaloalkanes. The reaction gets accelerated in the presence of light or halogen carriers. Addition of water. In the presence of sulfuric acid, 42% and 1% mercuric sulfate at 60 degrees centigrade, alkynes add on one water molecule to give aldehydes or ketones. For example, ethine gives ethanol and propine gives acetone. Polymerization. On heating, alkynes undergo polymerization in the presence of catalyst. The nature of products depends upon the conditions. For example, when ethyne acetylene is passed through a hot copper tube, it polymerizes to benzene. When passed through a solution of cuprous chloride in ammonium chloride, ethyne undergoes linear polymerization. Did you know? Markovnikov's rule was formulated by the Russian chemist Vladimir Vasilievich Markovnikov in 1870. Mechanisms that avoid the carbocation intermediate may react through other mechanisms that are regioselective against what Markovnikov's rule predicts, such as free radical addition. Such reactions are said to be anti-Markovnikov, since the halogen adds to the less substituted carbon, exactly the opposite of Markovnikov reaction. Again, like the positive charge, the radical is most stable when in the more substituted position. Summary. Let us summarize what we have learnt. Alkenes are class of hydrocarbons which contain only carbon and hydrogen. Two other terms which describe alkenes are unsaturated and olefins. Unsaturated hydrocarbons contain either double or triple bonds. Alkynes, like alkenes, are unsaturated hydrocarbons with the general formula CnH2n-2. They are very unstable and quite reactive. Alkenes and alkynes undergo addition reactions, which are mainly electrophilic additions. Alkenes exhibit geometrical cis-trans isomerism due to restricted rotation around the carbon-carbon double bond.